Good. All right. So we are happy to have Linhui Shen, currently at Michigan State, and he will speak about cluster nature of quantum groups. And Lina just posted his notes in the chat. Please.
Okay, thank you very much. And it is my honor to talk here. So let me share screen first. Okay, so I will be going to talk about some cluster nature of quantum groups. So we'll start with some basic setup. So suppose G is a complex group of type ADE. And I will assume it has trivial center, with trivial center.
You mean algebra group of type ADE? Yeah. So
yeah,
like
and I assume it's over C.
All right. Okay. Good. Yeah. Okay.
And so G, for example, G is PGON of C. Okay, and then this locus G is just the Lie group of Lie algebra associated with G. And then we can also consider some quantum group UQ of G. So this is a quantum group. First introduced by Jinfeld and Jimbo. And it's also called the quantized, the universal invariant algebra.
So Q is a complex number or what?
Q is, right now it's just a formal variable. Yeah. So universal invariant algebra. Actually, this. So let me make a comment that I assume this is over C, but it's not that important. You can assume it's an algebraic group as well. So it's a universal invariant algebra of G. So it can be defined using some explicit formula. So here is a formula that we have. So you can consider something called a Drinfeld double associated with Weyl. So this is generated by EI, FI, and KI tilde. You can also inverse those Ks. And so those generators will satisfy the following conditions. And here, this A is just the Gadan matrix. Okay, and so now if you quotient out the further relation that Ki times Ki tilde is identity, then you will get the quantum group. Okay, and so the main goal today, we want to somehow present a rigid cluster model that realizing this UQ of G. So more precisely, I want to realize this UQ of G as some sub-algebra of a quantized cluster algebra. And then we can use some cluster theory to construct which we call the cluster canonical basis for this UQ of G. And this basis will satisfy several nice properties because of the cluster theory. Okay, so that's the main goal today. And so now I want to introduce some the main tool or model to study this. This is called, the second part is called the modular space of G local systems. So first of all, we consider a surface S. So this is an oriented surface with boundary. And we also have punctures inside. So, so those 2 points here are called punctures. And we also have some marked points on the boundary. So these are called marked points. Okay. And so
are they ordered somehow cyclically or in any other way?
yeah, they are ordered. So I mean, we haven't maybe. Okay, so those are some just a geometric data, and then we can introduce a modular space. And so this was some work of Goncharov and myself and a few years ago that we introduced this modular space, which we called a PGS. So G is a group and S is the surface here. And it consists of 3 pieces of data. So the first piece is you get some G local system L over S. And then we'll also plus the second piece of data. This is a choice of a flat section of this associated bundle. So you can change the bundle, G bundle over S by some flag variety, and then you choose a flat section for each marked point, and also puncture. Okay, and then plus the third piece of data is so this is a choice of a pinning for every boundary interval. So this is the whole the triple of data that we considered, and of course module the
well, what is spinning?
Yeah, so I will explain very soon. So maybe a few remarks.
It's not just sort of an isomorphism which allows you to identify this values of sections and the endpoints.
It's essentially just a choice of a Chevrolet basis, so, which I will show very soon.
Yeah, maybe you explain it later.
Yeah. So if we just consider if you just have the first piece of data, a G local system, and mod G, this is nothing but the usual character variety. So you consider the homomorphism from pi 1 of S to G and quotient of G.
And this is not a cluster variety.
This is not. So the point is, this is not a cluster variety. And so then Fock and Goncharov they introduced some space, which is the first piece of data plus the second piece of data. So namely, besides this local system, they also have a choice of flat section or flag for each marked point and puncture. So it's like, they call it framing, a quotient of G, and there's something they call X space. So this is essentially just a Fock-Goncharov space.
Do you consider full flags only?
Full flags, yes.
Okay.
Yeah. So these are because I'm considering a flag section of G mod B here.
Yeah.
Okay, so in this sense, so we just add the third pieces of data, which is called pinning. So this is our space P, and so it is somehow an enhancement of the Fock-Goncharov space. And kind of a spoiler here is this one is class variety. This X space, and this one is also P is also a class variety.
So I'm a bit confused. You said from the very beginning that your G is just of AD type, and
yes.
I do not see what is special about AGE.
Yeah, so
this
at this moment,
general.
G could be any simple type. It's fine.
Yeah.
So
all right. And another question is, I don't know what the pinning is, but 1 and 2, they naturally appear if we think in terms of d-modules on curves with irregular singularities. It's kind of a Stokes data. But if is there any kind of Riemann-Hilbert type isomorphism of this PGS with some DRAM moduli space?
I don't know. I think yeah. I mean, I wanted to say yes, but I'm not good enough to confirm that.
Okay.
Okay, so maybe I can show some examples and then it will be clear what is a pinning. So if you consider T is a triangle, namely it's just which will serve as a local model for us. So it's you can view this as a disk with 3 marked points. Then the first type of data is trivial. There is no local system because the pi1 is trivial. And so then when we say a choice of flag, you just assign a flag to each piece. So you have B1, B2, B3. So those are flags, or maybe so BI. Another way is they are Weyl subgroups of G. And we further assume they are of a generic position, meaning if you consider B, any pair of them, say B1, B2, their intersection is commutative. It's a Gadan.
So I assume that your construction non-trivial even for PGL2, yeah, because there is non-trivial quantized enveloping UQ of SL2, which is the same as okay. So which means that in this case, your barrel, whatever your flag is just a line, yeah, or what? It's a point on CP1, so it's 3 points on CP1, and what means generic here?
That means they're different.
Just different. This is okay.
For CP1, they're different. Yeah.
Okay.
Yeah. And so then yeah, so and then we will have a pinning. So you have P1 and P2 and P3 associated. So when we say a pinning, this is just a PI. This is a choice of Chevalier basis.
So what do you call Chevalier basis?
Just
it's SL2 triple for I don't know what is
SL2 triple.
For SL2 is just SL2 triple. Otherwise, it's more complicated. You have more roots.
So, but you have to fix a pair of like opposite Borel. So when we see Chevalier basis, it's with respect to bi and bi plus 1. Okay.
And
so
I should think of them as opposite barrels, or what?
Yeah, opposite barrels. And you have to somehow fix the choice of like a basis. Okay, so here I put some matrix here to save some time, but which will appear later. Okay, so maybe in SL2, so there are just 3 lines, 3 points on say B2. So that's just B1, B2, B3. And so when we say a pinning between B1, B2, this is just, there is another line that we identify, defines isomorphism between P1 and P2, like something like this. It's the same as a choice of SL2 triple with respect to B1 and B2. Yeah. So what we get essentially is just this data and with a basis on every interval. Okay. So that's the case for a triangle. And so the main reason why we introduced the pinning we think this is an important enhancement of the usual X space is, so you can, if given some pieces, say with one pinning here, and some other pieces of other surface with another pinning, so then you can glue them together by identify those pinning. So therefore you can glue different surfaces. So in particular, you can glue the surfaces by using those elementary triangles.
What do you mean identifying pinnings? It just, for example, for SL2, it's just a choice. It's isomorphism.
Yeah, so there is a unique G that takes this pinning to this pinning because of the choice. If your G is adjoint, it means your center is trivial. So there is a unique element. Take this kind of basis or the pinning here on the left-hand side to this. And so then you can just define some gluing map by identify those pinning.
But when you glue together, this pinning disappears, or this edge.
Yeah, the pinning just appears. This pinning appears.
No. When you glue together, they just cancel each other, or you consider triangulated surface with a pinning associated.
Yeah, so if you just consider the usual flag, say you have B1, B2, B3, and the other pair of like other triple of flag. So there are different ways to gluing them because there is a quotient by G. So if you have like 3 points on P1, the other 3 points.
When you choose this G, so then it disappears, the sticky structure disappears.
Yeah.
Okay.
Yeah, but if you have this extra pinning data, then there is a unique way to glue them. So you will get like 4 points on P1. Maybe it's like a choice of basis. And okay, so then you can just build the whole theory on surface by studying basics on those triangles, and those triangles indeed will be our building block. And so okay, still need some space.
But so far there are no punctures, in the story.
Yeah. So the next example, which is more important to talk today, is we consider a once punctured disk. With 2 mark points. So it's like so it's a one puncture and two marking points on the boundary. So as we showed, there are some pinning data, P1, and the other pinning data, P2, and there is a choice of flag B1 and B2 here. And so, and associated with the puncture is another choice of a flag B. So the data is as following. If you consider the parallel transport taking this P1 to P2 along this line, then you got some Borel B1 or up triangular matrix in, and then if you're going downstairs, you get some B2. And when you assess some flag associated with a puncture, you assume that this flag is invariant under the monogamy. So that means B1, B2 inverse belongs to this Borel.
So can you repeat the geometry? So you have B which sits in the puncture, and the pinnings, they are not flags. Yeah.
Pinning are like associated with the boundary, but with respect to.
Yeah. You said that it's choice of Chevalier basis. It's not really the flag, it's something else. Yeah. What do you call parallel transport of the pinning? Or you transport the flag? I somehow missed.
So you should view this the pinning as some data that containing B1 and B2 and together with something here. So another way to see this is the following. So your flag is like in type A case. So your B1 is just some flag, say F1 containing F2 and so on. And then your B2 is another flag, say H1 containing H2 and so on. And so then you will get, if they are generic, so you can consider Fi intersect with Hn plus 1 minus I. This will give us a line. So then you will get a line decomposition of some vector space. So a choice of pinning is like a choice of a basis for every line.
Mm-hmm.
But it's a basis with respect to this on the left. So now because we have some local system here, so you can there is another pinning on the right, and then you can consider comparing them. So there is a parallel transport called P1, B1. We'll take P1 to P2 this way, and there is another which is B2. Okay, so essentially, so in this case, space BG, our P space is the same as the triple where you have a B1 and B2 and also a flag. So it belongs to okay, so you have B1, B2 are, so B1 belongs to, for example, up triangular matrices, and B2 is a lower triangular matrix. And you assume that B2 inverse times B1 is contained in the Borel subgroup, which is the data here in the middle. Okay, so and you can also compare this with the usual gross integral resolution. So you have G, and then I really shouldn't. Okay, maybe I should add. Okay, so yeah, so here maybe a quick remark is we can compare this with the gross integral resolution. So usually you have a group G, but you can consider something called G hat. And so where G hat consists of pairs, you have a G, and together you have a Borel subgroup or a flag that is invariant under the action of G. And so this generically, this is like a W. W is a Weyl group to 1 map. So for every G, there is a W torso here. In other words, the Weyl group X on G hat, okay, by just changing the corresponding B. So in the case of SLN, for example, so for every G, you have generically there are n many different eigenlines. So when you say a choice of B is just an arrangement of the eigenlines, so and generically there are n factorial many, which corresponding to the Weyl group, which is Sn in a case. Okay, so this is some basic example of our P space. And so the main result is that, so this is a work again of Fock-Goncharov and myself in the same paper. And I also studied some enhancement of this here. So it says that the ring of regular functions, so of this P space, this is a cluster Poisson algebra. And therefore it has a quantization. Which we denote by OQ of PGS.
So now I'm double confused. So first, in Fock and Goncharov, they did not consider the spinning, but their cluster varieties, like spectrum of this commutative algebra, they also had the quantization.
Yes.
Do I remember? Okay. So then you do not need this spinning just for the purpose of quantization. And second confusion is that this Q, maybe I forgot, but I think it should be a number, not a parameter. And for them, it is important, if I remember correctly, because they want later representations in some Hilbert spaces, some star structure on the algebra. So then probably, maybe at this point it doesn't matter, but later probably you should specify your Q, what kind of number will it be?
Yeah, so, well, to the first question, so the Fock-Goncharov considers the X space, and they showed that this X space is a cluster Poisson variety, but they didn't show that the coordinate ring is a cluster Poisson algebra. They just introduced some nice coordinates to this X, and they showed that there are some, when you flip the diagonal from one triangulation to the other, they behave like cluster mutations. And actually,
but they quantized those coordinates, they introduced this quantum torus.
They quantized, and we are using the same quantization as
okay.
And second, so they actually only consider the case when G is type A. So G is PGLN. Then they have the cluster structure. For general G, they don't actually. And so here, when I say, so I put the data here. So the first piece of paper, we do the same for the P space. There is a cluster coordinates. And so in the second paper, And so I showed that the coordinate ring is exactly the class algebra. And so as a second question, maybe, oh, sorry, so what's the difference between P space and X space regarding the cluster coordinates? So there is something called frozen variables. Namely, those are variables, but you will never mutate them. So the difference between P and X space is that we have some frozen variables associated to boundary. So if you forget about the pinning, so there is a map from P to X, but just forget about the pinning, then you just delete all those frozen variables. So in other words, we introduce some extra coordinates, which is corresponding to the pinning, and we use them to glue different surfaces. And then regarding this P, so far it's just a formal parameter. It doesn't matter because I didn't consider representations of this. But indeed, in the work of Fock-Goncharov, when you consider their representation as on some Hilbert space, there is some conditional here. But in this talk, I will not consider that. I don't know if that is.
Mm-hmm. Yeah, thank you.
Okay, yeah. So now I will talk about what is the cluster algebra, a quantized quantum cluster algebra. So indeed, I will use this the Fock-Goncharov quantization. So there's a Fock-Goncharov quantum cluster algebra. So I will start with something called a seed. So combinatorially, this is just something is an ice quiver Q. So I think I'm using a different quiver. Yeah. So I'm using this quiver. So we label the vertices of quiver 1, 2, 3, 4. And so there are arrows going from one vertex to the other. And so I put this box here. This means those are something called a frozen quiver. So I will never mutate that. And we allow some dashed arrow between frozen quiver. And dashed arrow means this is of weight a half. Okay. Then associated to this quiver, you can get something called an exchange matrix. It will be a 4x4 matrix. I think I do have a matrix here. Yeah, so it's a 4x4 matrix, and the sign which just indicates this sign just indicates the direction of the arrows. And here I put a half here, this corresponding to this dashed arrow here. So for any quiver like this, we will get a skew symmetric matrix, and then we can further quantize this local seed. So I consider some L. This is a Laurent polynomial ring over the variable square root of Q and its inverse. And then you can consider TQ. This is an L algebra, which are generated by those xi and its inverse, where I are just the vertices of the Q, and then with relation that if you consider xi times xj, this is Q to the power 2 epsilon ij. Epsilon ij epsilon ij are just the entry of the exchange matrix, and then xj, xi. Okay, and so the data associated with the quiver, which is a triple, it's a quiver Q, together with the algebra and the generators xi. This is called a seed.
So you started with the quiver, but
yes.
How to read the quiver from the geometry, or I shouldn't think in this way? Because you started with the quiver, you constructed some geometric object, something like quantum torus, classic Poisson torus. Yeah, but you started with something else. You started with the Riemann surface and some puncture.
So later I will associate a quiver to every Riemann surface if given a triangulation. And then you can just locally define some quantum torus to that. And each x will become the coordinates of your modular space.
Okay.
Yeah, but this is just some algebraic approach. You can do with any quiver. You can just define this triple. And then the important thing is one can do mutations of the quiver. So each mutable vertex k, mutable means those are not frozen. So in this case, 1 and 2 are mutable, but 3 and 4 are not. This will give us a new quiver, a new seed. It gives a new set of variables called xi prime, and such that so this xi prime is equal to xk inverse if I is not equal to k, and this is equal to xi times the product. Here r goes from 1 to the absolute value of epsilon rk. You consider 1 plus q to the 2r minus 1 xk. If this epsilon ik is negative and k is not I, and otherwise there is some other formula. It's also from epsilon ik, but it will become xk inverse and then inverse again outside otherwise. So this is an explicit formula for finding these new cluster variables. And there is a deeper reason why we define this way by considering some quantum dialogarithm, and its conjugation will give us this. But I will just skip that part just to give this formula directly. So now we can use, sorry. So now we can use this new set of variables xi prime to get a new quantum torus. So if you consider xi prime times xj prime, and so you will still get some q to the certain power of epsilon ij prime, then xj prime, xi prime. So in other words, those new variables are still q commutative. And so in this way, we will get a new quiver, q prime, that are given by this epsilon ij prime. And this is somehow called the quiver mutation associated with q. Yeah. And so putting them together, we get a mutated seed. That's delta mu k of q. This is given by this q prime and this quantum torus algebra and together with generators xi prime. So we can do this recursively, starting with one quiver. We can just mutate at each direction, like infinite many times. So essentially, we get infinite many seeds. And so then you can define the quantum cluster algebra, which I denote by this OQ sigma Q. By considering the intersection of all the obtained quantum torus algebra by doing mutations at each direction. Okay, and so the classical, semi-classical limit of this quantum class algebra is just the usual cluster Poisson algebra of Fock-Goncharov. Okay, so then maybe one more page here. Okay, so then there is a theorem by Davidson and Mendel, which is based on the work of Koncevich and Yan. I think it's also based on the work of Gross-Hakin, Kiel, and Koncevich on the study of scattering diagrams. So one can find a canonical basis for this algebra. So, but it is based on some technical condition. So if the mutable part of this Q admits the so-called reddening sequence, then the quantum cluster algebra has a natural basis, natural L basis. And furthermore,
L is some range, I forgot, Laurent polynomials.
Yeah, L is.
Okay. Mm-hmm.
Yeah, and furthermore, this basis is equivalent under the action of its so-called cluster module group. The action of cluster module group. Cluster module group is generated by, so when you do mutations to quiver, and sometimes you will go back to the same quiver, but with different variables. So those kind of mutations will give us a group, and that's called the cluster module group. And another comment here is I'm talking about something called a reddening sequence, which was first introduced by Bernard Keller, motivated by the work of Koncevich and Yan on the study of Donaldson-Thomas theory. Yeah, so okay, and so we will use this theorem in particular to get some. So later I want to show that the quantum group can be viewed as certain cluster Poisson algebra, quantized cluster algebra, so it will have a basis. And so here a few more examples.
Sorry, and the basis in quantum group which you are talking about, what is it?
What is it? Okay, so I will show that the quantum group can be realized as certain quantized cluster algebra.
Yes.
And then for that particular case, we showed that it also has a reddening sequence. So that quantum cluster algebra has a basis, and therefore we get a basis for the quantum group.
Yeah, but what kind? There are, there are many famous bases in UQ of G. So which one?
Well,
This
first of all, you have the canonical basis for UQ of n, Lustig's basis, and you also have some versions of them, like
you
in
mean UQ SLN, yeah. Or what is N?
UQ of n is a nilpotent part.
Ah, okay.
And here we consider UQ of G for the whole.
Yes. Okay, so this is a canonical basis, yeah, what we are talking, this.
Actually, it's a new basis, but I don't know which basis it is.
It's a new basis. It's not canonical basis, not some standard basis. It's something new.
Yeah.
Oh, okay.
So for UQ of G, there was also some work by Berenstain and Greenstein
Yeah.
called double canonical basis. And so
Yes.
I verified that when G is SL2, they are the same basis. But for general G, I don't know. I think they are different, in fact.
So then hypothetically it can be a new basis in the
Yes.
quantizing well. Oh,
Yeah. But
okay.
if you just restrict it to this part and consider its commutative version, then you will get something. So I think there was a conjecture of Joe Chemnitzer. This is the same as the usual Milkovich-Villona basis, which arising from the study of geometric Satake.
So it corresponds to some perverse shifts on the affine
Yes.
Grassmannian.
So there is something called Milkovich-Villona cycles, and yeah.
Oh, interesting. Yeah. Okay.
But yeah, in general, I mean, you can construct this basis, but it's very hard to describe what it is. It satisfies many nice properties. For example, the structure coefficient will be positive, and it's also invariant under the action of braid group action, and so on. But still, it's very mysterious.
Okay.
Yeah. So now I want to show its connection with the quantum group. In particular, what is a cluster structure associated with this PG? Say T first. T is a triangle. So when G is say PG 4, then the quiver associated with this is this guy.
So how do you read this quiver from the surface with marked points and some extra structure?
Yeah, so we really should consider this as a triangle. And then for PGL4, you just consider some refinement of the triangle by introduce this. And so if you just consider the usual X space, it will see just corresponding to the inner part. So there is no frozen ones here. So when we consider pinnings, so there are 3 pinnings. So each piece is here will corresponding to a pinning. And so and then the next question is, how do we get this quiver in terms of some structure from G? So it's corresponding to reduce the decomposition of the Weyl group element. It's the longest Weyl group element of G, and then you can, it's fairly complicated, but there is an explicit way to construct a quiver like this. I don't know if this makes sense, but here is another example. This is, I believe this is the quiver for P and SO8, which is the type D4 quiver. So again, there are 12 frozen variables. And so those bugs, for example, this 4 variables were corresponding to the pinning here on this edge. And the other 4 here corresponding to this side of pinning, and so on. Okay, so this is our local data. So for every triangle, you can explicitly construct some quiver. You can also explicitly construct some coordinates by interpreting as some cross ratio. And then we have to check that this is really independent of the choice of the longest decomposition, as the decomposition of the longest word. So and then it's actually a canonical choice. Okay, so that's somehow the local piece of quiver for a triangle. So now if you want to get, for example, a punctured disk, for example, I'm considering the space PGL4 and associated with a once punctured disk with 2 marked points on the boundary. So we can view them as the gluing these 2 pieces of triangle, the left one and the right one, along those. And so correspondingly, you have 2 pieces of quivers. So the left-hand side is just corresponding to, so this part of a quiver here. And there is a similar, like you can take a mirror of this, get another piece, and then you glue them along the corresponding frozen variables, which will cancel those arrows. So they are of opposite direction, so they will get canceled. So eventually for this PGL4 associated with the once punctured disk with 2 marked points, you just get this quiver. And you can do the same for a general surface. So basically you just cut them into different triangles. And for each triangle, we have this building block here. And then you just glue them along the edge by identifying the frozen variables.
So I'm a bit confused. So when you are talking about UQ of G, does it mean that your geometry is standard? It's something like disk with 1 puncture.
Yes, it's a disk with 1 puncture and 2 marked points.
Yeah, okay, which means that whatever is related to quantum groups is just this simple geometry, but you can change this G. And
yes,
if you change the geometry as well, you get some new quantum algebras. Okay. Mm-hmm.
Yeah, so if I just consider this surface, so this guy eventually will correspond to this UQ SL4. I mean, this quiver. So you
this is always the case. If I want, like, I don't know, UQ of some G, I consider the corresponding simply connected group and kind of use this geometry puncture disk with 2 marked points, 2 pinions, and do whatever you say. Okay. Mm-hmm.
So in fact, this one has a group structure. So you can, for example, you have once puncture with pinning. And so you can multiply them together by just identify those 2 pinnings. So you'll get something with 2 marked points. And then you can cut a loop. And then this will becomes, again, a once puncture disk with pinnings. So in this way, you can define some like multiplication.
And probably you have a co-multiplication as well.
Yeah, when you consider, this is actually a co-product, because when you consider functions there, it's actually pulled back. So the functions here will pull back to here. So it's a co-product of the corresponding quantum group.
Mm-hmm.
Yeah. And then you can also consider the inverse by just rotate reflect this matrix, this disk. And so the point is all the structures from the quantum group can be just geometrically interpreted by playing with this model. Okay, so I have only 4 minutes left.
No,
so,
you can go the time if it's
yeah, but
necessary.
I have to go actually.
All right. Yeah, all right.
Okay, so maybe let me just summarize the result here. So we just show that you can consider this the quantum quantum class algebra, and then you can consider the Weyl group invariant. So because you can change, as I said, that you can change the flag associated with this guy. And so this is exactly this TQ of B. This is Junfeld double. And so now you can also quotient out some automorphism. So there is a special center which can also be interpreted as by using this language, but I don't think I have time. So you can quotient out this, and you get this UQ of G. So here I have to assume that G is simply laced, so type ADE. Because somehow I have to use the result of the Mendel and Davis and Mendel for the case when the quiver, it has to be skew symmetric, not skew symmetric. In other words, for non-simply laced case, you don't have a quiver. You have to replace this by something like weighted quiver, but still it's not developed yet. Okay, so here we got this, and then you can, as we said, there is a basis here, and you can consider, and one also need to show that this Weyl group action, and there is also a braid group action, which they are all XY as cluster module group elements. So they will preserve the basis. So the point is braid group action. And Weyl group action. Cluster transformations. So they will preserve the basis, and therefore you get a basis here on OQ of G, which has a structural coefficients and which are equivalent under this section. And another comment is, so talking about this braid group action, I think it was first considered by Yan here, and then there was also some. I think I'm not quite familiar with the history, but I think Lustig also give a formula.
Yeah, Lustig also, but there is a question related to it, because in my story, this braid group action came not from just appeared not an automorphism of UQ of G, but appears as certain elements, certain functionals on the dual Hopf algebra, which mean that I quantized not only the action of the braid group, but also the Weyl group itself, the elements as generators of the braid group, which mean that in particular to each vertex I of the quiver, I had the quantized simple reflection, say SI, and not just a conjugate with it. And in particular, I could compute the square, like SI squared, which of course not equal to 1, but something else. And so I'm just wondering whether there is a place for this. I spoke to Sasha at IHS probably this summer or last summer, I forgot. So I think maybe I asked him what's analog in this geometric story of the actual quantized simple reflections. It's no, I mean, it's kind of, because it looks like the language you propose is very adequate, but then you should incorporate everything, including quantum Weyl group itself, not just the braid group action.
Yeah, so maybe one comment is about this braid group action, we give a geometrical interpretation. So remember, we have a pair of flag here, say B and B prime, and there is puncture. And so you can consider a chain of flags with respect to this here. So those are just like your B plus and B minus, and then you can consider something in between. So there is a unique decomposition. So you get a few of intermediate flags, B1 and so on.
They depend on the choice of the reduced expression of the longest element.
Depends on the choice of reduced expression.
Okay.
Yeah. So another quick way to view this is your V B could be something like L1 considered in L2 tensor with L2 direct sum with L, something like this, and then B minus is like going backwards. Ln is considered as this, and then you can just adjust the different orders of L. You get different flags, which depends on the choice of decomposition of W node. But when you fix an I, there is a choice of a B here, which is essentially you just, for example, in this type A case, you have L1, the same everywhere, except until the I1, you should replace this by I plus 1. So you get another flag. And similarly, you will get another flag here by consider the other pair. And then you just rotate this disk slightly. You replace this P by this new P. You replace this B by this new B and this B by this new B. You will get a automorphism of your P space. And we showed this is the same as the braid group action on the quantum group. Okay, I think I have to stop here. Thank you very much.
Yeah, thank you very much. It's very interesting talk. We have your slides and there is your paper in the arXiv for those who want to learn more questions. Actually, you see this splitting. I mean, certainly there should be interpretation of this pinning in terms of this irregular, well, Deligne-Malgrange or whatever version, Riemann-Hilbert correspondence. Because this Deligne-Malgrange, you have a regular D-module like meromorphic connection, and you have a local system on your curve with certain additional data, like incorporated in Fock and Goncharov. It's just covariant flags, maybe full flags. But then it looks like you choose splitting, like, well, I'm talking about a series A, like AN, and then you choose indeed the splitting of the flag. These things, like the last one, which in red on your last page, they somehow similar things appear in our story with Maxim on irregular Riemann-Hilbert.
I think I've also learned some work like on the Stokes data, and there is also So it's related to the Poisson-Ledoux group, and there is also a rotation, which I think is
Yeah, in the simplest case, yeah, it's probably Bolch like
yes,
20
yes.
years ago, yeah. But there is kind of a more general consistent picture, which somehow probably it has nice interpretation in terms of the Fukaya categories, because of the work of Shen, Treumann, and Zaslow, which allows to realize irregular Riemann-Hilbert in terms of certain brains like Lagrangians with rank 1 local systems and the cotangent bundle to the curves. So
Yeah, so I
yeah,
think for that we have some work. So it's with Zaslow and also Lan Ying and a few like Roger
yeah,
Cassel and so on.
maybe, yeah, I
So,
don't
I mean,
remember.
it's some of my recent work with them. It's not written yet, but the idea is there is also a braid group action. So we should consider some Lagrangian knot.
Yeah,
So locally, it's there is some. So you can. This is a front projection. So you have some data like this. This is unknot, but it's passing through some lines. So the idea is you can shrink this one and passing through here, exchange them. So you will get I mean, it will end up with the same knot, but it will induce an action on the Shandy Schumann Zaslow's modules.
Yeah. I'm started to recall what we did with Maxim. Yeah, it's related. It's related to wall crossing in the corresponding Fukaya category. Yeah, and these Legendrian knots, they are contact boundaries of some Lagrangians at infinity. Yeah.
Yes,
Which probably it should be, because after all these mutations, it's an example of the wall crossing. I mean, this wall crossing transformations. Okay, great. Yeah, it's very interesting indeed. And one thing it's rather remark, I mean, it's pure algebraic geometry, like in Fock-Goncharov, but there is this non-abelian Hodge theory of Simpson, yeah, where you need to use some real numbers, and these character varieties or their versions, they are just spaces which you put the generic point, but okay, what I mean that there is an extra parameter in the story which kind of you fix, and Fock-Goncharov fix, because you work with a fixed space. You do not consider say one parameter like twistor family of these generalized, let me call them generalized character varieties, yeah. But if you do, then over C star you have a local system of non-linear, I would say, local system of spaces like your PGS, but you should also add something at 0 and infinity. And so this sort of a tricky, it corresponds, in the drum language, it corresponds to degeneration of lambda connections, possibly with irregular singularities, to Higgs bundles with irregulars. But it's not easy to spell it out if you, on the Betty side, if you work with character varieties. So I don't know what's happened to these filtrations, spinnings, what's happened in that degeneration. So anyway, more questions? Well, if there are no more questions, so let's thank the speaker. Thank you very much. Very interesting talk, really. And maybe you will send this final version, but I don't know. Your notes contain more. Yeah, they contain more. Okay. All right. Thank you.
Okay. Thank you very much. I think I really have to go now.
Yeah. All right. Okay, good luck.
There was some question about the arXiv number of my paper, but it's in the
they already found something, yeah. Oh, so, okay, great.